23 of our series on numerical methods in civil engineering. We will continue with our discussion on analytical techniques for solving second order linear partial differential equations. Last time we looked at methods for solving hyperbolic partial differential equations, and specifically we looked at the method of eigenfunctions, and we started looking at the method of characteristics, which yields a lot of geometric insight into the problem of solving the wave propagation problem in a space-time domain. Specifically, we said that given any point in the space-time domain, any point x0 t0 in the space-time domain, I can find the solution to the wave equation at that point based on the initial conditions. When the initial conditions are prescribed at time t is equal to 0, then it depends on the part of the t is equal to 0 axis, which lies between these two lines x with slope plus c and minus c. So, all the information, all the initial information in this part of the domain within these two black dots can affect the solution here, right. In addition, we said that to affect the solution at this point, right, any source of disturbance, it should be able to traverse the path between that source and this point, right, and that path must lie along the characteristic lines, then that path must be able to traverse that path within the time t0, right. If it is not able to traverse that path within the time t0, that means that source will not affect the solution at time at the point x0 t0, right. So, for instance, if there is some disturbance at this red point, for that to affect the solution at x0 t0, it has to traverse along the characteristic lines passing through that red point, that is these two lines, these two yellow lines, and once it reaches points on the characteristic lines passing through x0 t0, this information can propagate from these blue dots to this line, right. So, the disturbance here goes and affects the solution here, and the solution here affects the solution here, because the information from here can go to can affect the solution here, because it is passing through the same characteristic line, right. But the sum total, the net path from here to here must be able to traverse this net path from here to here within time t0, right. If it is not able to do that, then the disturbance here is not going to affect the solution at x0 t0, right. So, the information travels only along the characteristic lines, number 1, and the information travels with the speed equal to the wave speed, right. So, those are the two things we can take away from here. So, we said that for this point x0 t0, this shaded area in gray is the domain of dependence, right. The solution here depends on things happening within this domain, right. Disturbances, initial conditions, anything happening within that domain is going to affect the solution at x0 t0, right. Similar to the domain of dependence, there is something called the domain of influence. It is basically just the reverse. I say that points, this tells me if there is a point in the xt region, in the xt domain, what is the part of the domain which affects the solution at x0 t0, right. So, the solution here depends on this region. This is the domain of dependence. The other way of looking at it is to look for the domain of influence. Suppose I have a disturbance at a certain point. What is the conceivable region in the space-time domain which the disturbance at that point can affect, right. So, that is the domain of influence of that point, right. So, similar to the domain of dependence, points on the initial line, say t equal to 0, have a domain of influence comprising the part of the space-time domain where the solution is affected by the value of f and g at that point, f and g being my initial conditions, f and g being my initial functions. So, characteristic lines emanating from a point x 0 on the t equal to 0 line will affect the solution at all points along their length, that we already know. Suppose I have a point on the t is equal to 0 line. So, any point lying on these blue lines are going to be affected by the initial conditions here. But what is also important is that any point in this shaded region is also going to be affected by the solution, by the initial condition here. Why is that? Well, you look at a point here, right. This point, the information from this point is going to move along characteristic lines passing through this point, right. Characteristic lines means lines with slope plus c and minus c. So, for instance, I do not have a point here, but if I bring my cursor here and focus on this region, right. So, information from here is going to move along the characteristic lines passing through that point, right. So, the characteristic lines passing through that point. So, the information here is going to travel in this direction, right. Similarly, the information here on the negative, on the other characteristic line is going to travel in this direction. So, the information here can propagate to this entire region, right, because this entire region is the region through which this information along this and along this line and this line can get propagated into this region, right, where two characteristic lines intersect, right, that in that region we can see the influence of this point, right. So, characteristic lines emanating from point x 0 on the t equal to 0 line will affect the solution at all points along there, that is a given. But these points in turn have their own characteristic lines, and once the information from x 0 reaches them, say at time t star, they will start emitting information along their own characteristic lines that will affect the solution at all points lying on those lines. So, the domain of influence is limited by the fact that a wave generated at some time at a point cannot influence events at another point in less time than it takes to travel the distance between those 2 points, right. So, that is how we find out the domain of influence. So, this was a general discussion of the method of characteristics. Let us use the method of characteristics to find the solution to this inhomogeneous wave equation. Why is it inhomogeneous? Because on this side you have a forcing function f x t, right. The previous wave equations that we looked at, they were all homogeneous wave equations. So, this is an inhomogeneous wave equation with f x t, a source term f x t, and in this case for simplicity I have assumed that the wave speed c is equal to 1, right. So, we will solve this problem subject to general initial conditions. So, up till now we have looked at initial conditions, meaning conditions on the line t equal to 0, right. That may not always be true, right. I can have initial conditions at any time, right. Suppose I have a problem, I specify the conditions at time t equal to 5, right. So, at time t equal to 5 I give some disturbance, I give some startup conditions, and then for time t greater than 5 that is going to propagate, right. So, the initial conditions need not be restricted at time t equal to 0, right. So, in this case I am going to subject it to general initial conditions that are prescribed on a curve gamma 0 on the x t plane, not necessarily on the initial line at t equal to 0. So, I have a curve gamma 0 in the x t plane, right. You can see that it is not aligned along the line t is equal to 0. So, on this curve I prescribe certain initial conditions, and you can see these initial conditions are not all at the same time, right. So, at any point on this curve, these are points where I prescribe the initial condition. So, at this point the space and time are given by x and t, right. At this point, another point on this curve, the space and time may be different, it may be at a different time, right. So, these are the points at which these are points in the space time domain where I give my initial condition, right. That means at different points they are setting off this at different times, right. So, I have a location in space, right. So, it is like, you can think of somebody has laid a charge in space, right, laid charges in space, right, and those charges are going off at different times, right. So, at different locations in space, the initial condition is starting at different times. So, not necessarily the initial line at t is equal to 0. Thus, we assume that phi and its nominal, we will find that we need not only to prescribe phi, that is the actual primary variable, suppose the displacement, but we also need to specify its normal derivative at gamma 0, right. So, to fully define the problem, not only do we need to specify phi along this red line, the variable, the primary variable, we also need to specify its derivative, how phi is varying in the direction of the normal to this line, right. How is phi is varying in the direction of the normal to this line at different locations along that line. So, these are the initial conditions that we need to specify along gamma 0. So, the negative characteristic line passing through any point x 0 t 0 in the domain are denoted gamma minus. So, these are the negative characteristic lines, this gamma minus, right, and these are the positive characteristic lines. So, here is my point x 0 t 0. Through this point I have these two lines, right, and these two lines each having slope equal to 1, right, 1 and minus 1 in this case, because our wave speed is 1, right. So, slope of 1 and minus 1 passing through that point, and these characteristic lines intersect my gamma 0, my initial line, right, my initial condition line along which I prescribe my initial condition, and the information from here is going to travel to this point along these characteristic lines with a speed of 1. So, all points on the negative characteristic line satisfy the equation x minus t equal to x 0 minus t 0 that we have seen last time, right. So, that is basically the equation of the negative characteristic line, x is equal to x 0 minus t 0 plus t, or x minus t equal to x 0 minus t 0. Similarly, we have the positive characteristic lines passing through any point x 0 t 0 in the domain denoted by gamma plus, such that all points on that line satisfy, all points on gamma plus satisfy the equation x plus t equal to x 0 plus t 0. To find the solution at x 0 t 0, we form the region R bounded by the initial line gamma 0 and the characteristic lines gamma plus and gamma minus as shown in the figure. So, we consider this region R, right, this region R, which is bounded by gamma minus, gamma 0 and gamma plus. Next, we integrate this equation, which is my governing equation, right, my governing equation, which I integrate that over the domain R, right, straightforward integration of this over the domain R, right. And then we consider, since my independent variables are x and t, my gradient operator is nothing, it comprises, its components are the partial derivatives with respect to t and x, right. So, gradient is given by del del t del del x. Then it is clear that the term within the integral on the left hand side of this equation is the divergence of phi hat, where phi hat, so if you look at this term del 2 phi del t square minus del 2 phi del x square, this is equal to the divergence, this dot of this gradient operator acting on a vector. And what is that vector? That vector is given by phi hat, where phi hat is equal to del phi del t minus del phi del x. So, if you take the gradient operator, which was del del t del del x, and you dot it with this vector del phi del t del, with whose components are del phi del t minus del phi del x, then you are going to get del 2 phi del t square minus del 2 phi del x square, like here, right. So, that is exactly what you are going to get. So, we can write this as this operator on the left hand side, this operator on the left hand side, I can write this as divergence of phi hat operating on the domain integrated over the domain R, right, integrated over the domain R, and then I convert this volume integral into a surface integral using the divergence theorem. So, I get divergence of phi hat is equal to phi hat dotted with n, and now the integral is over the surface, right, over the boundary of the domain, which comprises of 3 parts, gamma minus, gamma 0 and gamma plus, right. So, phi hat dotted with n, and then phi hat of course is del phi del t minus del phi del x dotted with n dl, right. So, now I have converted this integral over this region R to integral along these lines gamma minus, part of gamma 0 and gamma plus. So, in the above, gamma is equal to gamma 0 plus gamma plus gamma minus is traversed in such a fashion that while traversing along the curve, the outward normal n always lies to the right. If you go back and take a look, I am moving along this direction. So, the outward normal is always lying to my right. I move along this path, I move along that path, I move along. So, outward normal is always lying on the right, on my right hand side as I move along this path. And dl is the elemental arc length along that curve, right. dl is the elemental infinitesimal arc length along that curve. From the figure, it can be seen that the normal is actually given by dt dl minus dx dl. If you take a look, you can see here, right, the normal is minus dt ds, it has a negative component, right, dt, it is pointing in this direction, minus dt ds and dx ds, right. So, that is my normal, and hence we get this integral as minus del phi del x del phi del t dotted with n. For some reason I have just changed the order, but that is not important, right. So, minus del phi del x del phi del t dotted with n, and if I do that, I get minus del phi del x dt, this dl cancels out, right. So, I get minus del phi del x dt minus del phi dt dx, right. So, this integral, that is what I get. Therefore, we can write my equation, which was this equation, right, as this integral, right, and the integral of f of x t over the region R, right. So, now we are going to evaluate this integral along various portions of the boundary, right. So, first we are going to evaluate it along gamma minus, and along gamma minus you will see that this line has got slope 1, right. So, along gamma minus, as it moves along this direction, x decreases, as it moves along this direction t decreases, and the slope is 1. So, dx is got to be equal to dt, right. So, both have the same sign, dx is negative, dt is negative, right. So, dx is equal to dt. So, along that line dx is equal to dt, and we can write del phi del t dx plus del phi del x dt. Basically, this term is that now I can replace dx by dt, right, along that line. So, I get del phi del t dt, and del phi del x dt I can replace by dx, right. And if you look at this, what is it? It is nothing but the total derivative of phi, right. So, that is nothing but d phi. So, that is the integral of this over gamma minus, right, and d phi, and then if I evaluate that, if I integrate that and evaluate it at the two endpoints of my path, right, that is phi of x 0 t 0 minus phi of x minus t minus. Why is that? Well, because my path is going from x 0 t 0 to x minus t minus. Normally, it would be phi of x minus t minus minus phi of x 0 t 0, but there is a negative sign in front. So, I get phi of x 0 t 0 minus phi of x minus t minus. Similarly, along gamma plus, we can see that along this line we have dx dt, dx is equal to negative of dt, because as t increases x decreases, right, and the slope is 1. So, dx is equal to minus dt, and again we replace dx by minus dt and dt by minus dx, right, and eventually we end up with an integral, again a total derivative, right, of phi over along right, it's, pardon me, it's plus, right. Okay. So, then we integrate that, and when we evaluate the function phi of x 0 t 0 minus phi of x plus t plus. Okay. So, we have evaluated this integral gamma over gamma minus and gamma plus, but I have not evaluated it over gamma 0. So, that part is still remaining, right. So, what I am going to do is that I am going to substitute this in my this equation, right, and bring the integral over gamma 0 to the right hand side, right. So, here this left hand side includes the integral over gamma 0. I am going to include that, bring that to the right hand side. If I do that, I am going to get something like this: phi of x 0 t 0 is equal to half of phi of x plus t plus phi of x minus t minus, plus you can see that I have brought this integral to the right hand side, right, half of integral of del phi del x dt plus del phi del t del x over gamma 0 plus the source term, right. So, this is my solution. So, you can see that this expression actually generalizes the D'Alembert solution for the wave equation to situations where I have the initial conditions not prescribed at t is equal to 0, not prescribed along the t is equal to 0 line, and it is prescribed along any arbitrary curve gamma 0, number 1. So, that is the one modification, and the second modification is that I have a non-zero source term, right. I have this additional term f of x t, right, function, another function of f of x t, which is like a source term, right. So, for the non-homogeneous wave equation with non-standard initial conditions, non-standard meaning initial conditions not all given at t is equal to 0, this is my solution to the wave equation. So, for a general line, so I said at the beginning that not only must we know phi at on gamma 0, we must also know the component, the dot product of the gradient of phi in the normal direction. Basically, I must know the normal derivative of phi along gamma 0. Why is that? Well, to understand that, it makes sense to parametrize my initial line gamma 0. So, I suppose that gamma 0 I can parameterize in terms of a parameter s, right, and so at while moving from x minus t minus to x plus t plus, I am moving along gamma 0, right, and along that path I have a parameter s, right. So, x is actually a function of s, as is t a function of s along that line, right. So, that one line can always be, if I know the direction, I can always parameterize it with one quantity, one scalar, right, and what is that scalar basically? It is distance along that line, right. So, as I move along that line, my x and t changes. So, x is a function of distance along that line, t is a function of distance along that line, right. So, x is a function of s and t is a function of s, right, and here I have said that function is x 0 and t 0, right. X 0 a function of s gives me the x, and t 0 of another function of s gives me t, right. So, the unit tangent vector to gamma 0 is therefore dx 0 ds dt0 ds. It tells me how x0 is varying with s and t0 is varying with s. So, now you can see that now I do not have partial derivatives anymore, I have total derivatives, because x0 and t0 are functions of s only, right. So, this is my unit tangent vector x dot 0 t dot 0, where dot denotes differentiation with respect to s, and the normal pointing outwards as we move along the curve from x minus t minus to x plus t plus is therefore given by minus dt ds dx 0 ds. This we have seen already, right, and that is equal to minus t dot 0 x dot 0. Then if I know grad phi, which is del phi del x del phi del t along gamma 0, we can evaluate the partial derivative of phi with respect to x and t along gamma 0 by solving two simultaneous equations. If I know the gradient, right, I take the projection of the gradient along the unit tangent vector s, and that gives me del phi del s x dot 0 plus del phi del t t dot 0, right. If you calculate that, if you take the, this is my gradient vector, if I take the dot of this with this vector, right, x dot 0 t dot 0, I basically get this on the right hand side. Similarly, if I take the gradient of this vector and I take if I take the dot with this vector, I get this term, right. So, now we can solve for the partial derivatives, right, if I know these quantities, right. If I know del phi del s and if I know del phi del n, I can solve for del phi del x del phi del t del phi del x del phi del t, these two simultaneous equations for my partial derivatives which I am going to solve, right. And I of course know x dot 0 t dot 0 because I know the path, right. I know the path as a function of s, the distance traveled along that path. So, that I know. If I know my gradient, and if I know once I know my gradient, I can find out my del phi del n and my del phi del s by just taking the projection of my gradient vector along the unit vector along the unit tangent vector and the unit normal vector. So, those are those two quantities, right. So, if I know the gradient, I can find out my partial derivatives with respect to phi and t, right. So, that explains why I need to know not only phi along my line gamma 0, I also need to know the gradient along gamma 0, right, because in order to evaluate my partial derivatives, I need that information. Finally, one more point, it is, we note that if the slope of gamma 0 is such that dx dt is less than c, then gamma 0 will intersect the characteristic lines to x 0 t 0 at only one point, while if dx dt is greater than c, it will intersect the characteristic line through gamma 0 at it should be x 0 t 0 at 2 points. Sorry. So, basically what I am trying to say, I have tried to make it clear from this picture. So, if I have this x 0 t 0 point, right, and this is my either my brown dotted line or my green dotted line are my gamma 0, right. Suppose the characteristic lines through x 0 t 0 are intersect this line only at one point. The slope of this line is such that d mod of dx dt is less than c, so that the only one characteristic line intersects this initial line, right. In that case, my solution is going to break down, because my prerequisite is that both the characteristic lines passing through x 0 t 0 must pass through my initial condition line, right. So, this green line is fine, because both my characteristic lines passing through x 0 t 0 intersect this line, but look at the brown line. This line x is equal to x 0 minus c t intersects that line, but this does not intersect that line except at some time which is much beyond my time t0, right. So, that is not going to work, right. So, in this case the solution is going to break down. So, if I have a solution initial line initial gamma 0 whose slope is less than c, mod of dx dt is less than c. Now, how did I write that? Well, it is basically this, right. Mod of dx dt is less than c. In that case, my solution is going to break down, right. So, that is when the method of characteristics is not going to work anymore, right. Is that clear? Okay. So, that is all I had to say about analytical methods for hyperbolic equations, right. We looked at the method of eigenfunctions, which I mentioned that is a very general method, right. It is not only valid for hyperbolic partial differential equations, you can extend it to other types of partial differential equations as well, as we are going to see very soon. But then we looked at another method, which is the method of characteristics, which is sort of specific to hyperbolic partial differential equations. In particular, it is a very useful and very meaningful and very insightful way of solving the wave equation. But let us move on to parabolic equations, and let us look at the diffusion equation. So, a main example while we were talking about the canonical forms of the partial second order linear partial differential equation, I mentioned that the diffusion equation is a typical example of the parabolic canonical form of the second order equation, right. And a particular example of the diffusion equation is heat flow, is diffusion of heat through a metal, right, or through any substance which conducts heat, right. So, heat flow occurs due to the diffusion of energy from one part of the problem domain to another. The conduction of heat takes place through diffusion. So, if you have a heat source somewhere, the molecules there start moving more, right, they vibrate more, they move more. So, they have more energy, that energy gets transmitted over the domain, heat propagates, right. So, inhomogeneity in temperature means that the molecules at some region are at a higher temperature than at another region in the model. And basically what we want to do is to obtain the governing equation of heat flow, right. What is the equation which tells me how the temperature is going to vary across a domain, right, at the boundaries of which suppose I have a certain heat flux, right, or I prescribe a certain temperature, right. So, in that case, how is the temperature in that domain going to vary as a function of space, as a function of time, right. That is what I want to model, right. To do that, I use the principle of conservation of energy. And to make things simple, I look at a bar, I look at the heat conduction problem, the diffusion problem in 1D, right. I look at a bar which is of length L, and I assume that it is lying between x is equal to 0 and x is equal to L. So, the energy contained in a width delta x of the bar is proportional to the mass in that width, right. It is proportional to the mass in that width. So, why? Well, you know about specific heat capacity, right. If rho be the mass per unit length and C the heat capacity per unit mass per degree of temperature, then the heat energy in that width delta x is given by the density times delta x, which gives me the mass, right, times the heat capacity C times the temperature, right. So, that is the total heat energy in that width delta x, rho C T, right, rho C T times the volume, right, which is delta x. And we denote the heat flux passing a plane through x at a time t by q, right. So, this is my little width delta x, it is bounded by those two planes, and then I have heat flux through these planes, right. So, conservation of energy requires that the rate of change of energy in that width delta x must be equal to the net flux, the heat amount of heat in that little volume, it changes depending on the amount of heat that is flowing in through the boundaries and the amount of heat that is leaving through the boundaries, right. So, the rate of change of energy with delta x must be equal to the net flux, that is the difference of heat flux entering and leaving the with delta x at the ends x1 and x2, right. So, we see that rate of change. So, this was my volume of heat energy in my little strip, right, rho c t dx integrated over x1 and x2, that was the total heat energy in that little strip, and the rate of change of that heat energy is equal to the flux at x1 minus the flux at x2, right. And in the limit, when delta x goes to 0, right, what do we have? We have del t rho c t is equal to minus del q del x. So, this q x1 minus q x2, I can now represent it as del q, right, in the limit that x1 and x2 tend to 0, I mean x1 minus x2 tends to 0, and this integral becomes derivative, right. So, I get that, right. So, that is part of the problem. The other, next I have to look at the constitutive behavior. Basically, I have to introduce the heat conduction equation, right, which requires that heat flux be proportional to the negative of the temperature gradient, right. So, it tells me how the flux is related to the temperature. So, heat is going to flow in the direction from higher temperature to lower temperature, right, and the heat flow is going to be proportional to the difference in temperature divided by the, in this case we can think of distance, but in multi-dimension it's basically a gradient, right. So, if in 1D it is the temperature at x1 minus the temperature at x2 divided by the difference between the distance between x1 and x2, right. So, that is the gradient, and heat is flowing always in the negative gradient direction because it flows from higher temperature to lower temperature. So, and then we say that is so we know that the heat flux is proportional to the temperature gradient, negative temperature gradient, and lambda is the constant of proportionality. So, I can write heat flux is equal to minus lambda times del x t, right, and then I go ahead and substitute this in my equation here, which I got from energy conservation, right. This equation I got from conservation of energy. So, I go ahead and substitute del q del x in terms of lambda del t del x, right, and once I do that I get an equation like this, right. And then I assume that density and heat capacity do not vary, not always true, but for the sake of simplicity let me assume that the density and heat capacity do not vary with time and space throughout the bar. In that case I can pull this rho c down here, right. So, I get del t t is equal to del x lambda by rho c del x t. I denote lambda by rho c by kappa, right, and then I get a final form of this equation as del t t. T is the temperature, right, small t is the time, right. So, del t is equal to del x kappa del t del x, right. So, in order to, so this is my final equation, this is my diffusion equation, right, for heat flow. In order to get unique solutions, again we have to specify initial conditions, which tells me what is the temperature at time t equal to 0 in my domain, in my spatial domain, right. At time t equal to 0, how does my temperature vary in space? So, which is T0 x, which is a function of x, right. So, that is my initial condition. In addition, I need boundary conditions, and in this problem of our bar 1D bar, I am going to specify, I have two boundaries at x is equal to 0, x is equal to L. So, I am going to specify the temperature at x is equal to 0 and x is equal to L again as a function of time, right. So, T1 of t and T2 of t. So, these are very simple boundary conditions. I just wanted to mention in passing, like I also mentioned when I was talking about the wave equation, that the boundary conditions need not be as simple as that, right. We can have a mix of Neumann and Dirichlet boundary conditions. So, I can specify, I can have a combination of the temperature and the gradient of the temperature specified at 0. Similarly, I can have a combination, linear combination of the temperature and the gradient of the temperature specified at L. In this case, it is really simple because I am just specifying the temperature at x is equal to 0. So, this part alpha is equal to 0 and beta is equal to 0 for us, right. So, it is a straightforward Dirichlet boundary condition, but you can have a combination of the temperature as well as its derivative specified at the boundary, right. The most general form of the boundary condition, but even under these conditions it is possible to, the problem is still well posed and it is still possible to get a solution for the heat equation. We can generalize this to 3 dimensions, the 3D. I do not want to spend too much time on it, but just to mention in passing, we say instead of saying that Q is the heat flux through a plane, through a line at x is equal to x1 or x is equal to x2, we say it is the heat flux per unit area, where area denotes the boundary of a particular volume in 3D space, right. So, Q is the flux per unit area, then the flux through an element of area ds is, and with normal n is given by Q dotted with n ds, right. ds is the, n ds is my area, right. Area, magnitude of the area given by ds, infinitesimal area, n is the normal of to that area, to that infinitesimal area, and Q is the flux through that area. So, the total flux through that area is given by Q dotted with n ds. And next we consider an arbitrary volume V of material with surface S, and the heat contained in that volume V is again given by rho Ct dV integral of V, like we had earlier, rho Ct dx integral from x1 to x2. So, here we have rho Ct dV integrated over my total volume, right. And then we equate the rate of change, again we use the principle of conservation of energy, and we say that any change in the energy contained in that little volume dV, or any change in that volume V which comprises infinitesimal volumes dV, is given, the rate of change of that energy has got to depend on the how heat is flowing in through the boundaries, right, how heat is flowing in or how heat is leaving through the boundaries, right. So, del T integral of V rho Ct dV got to be equal to minus Q dotted with n ds, right. So, net flux through the boundary, right. And again we use the divergence theorem to convert the surface integral to a volume integral. So, Q dotted with n ds, I convert it into divergence of Q dV, right. Use the divergence theorem, I get that, and then I use, so interesting thing is that I do not want to spend too much time on this, but it might be worth mentioning in passing, is that I have this partial derivative with t outside the volume integral, right. Well, you can show using some arguments based on continuum mechanics, right, based on continuum mechanics, that it is possible to bring that partial even if my volume V is not constant, right, it is varying with time, right, it is possible to bring that integral inside, that partial derivative with respect to t inside that integral, right. And if we do that, I get something like this, rho c del t t plus divergence of Q integral over dV, that is equal to 0. And since this volume is arbitrary, for the integral to be always, this is true for all arbitrary volumes, right. So, I can make my volume go to a point, right, it has got to be true there. So, that means it must satisfy, and I can do that at every, for my every volume at around every point, centered around every point in my domain. And if I do that, in order to satisfy this equation, this must be 0 pointwise, right. So, rho c del t dt plus divergence of Q got to be 0 at every point in my domain, and thus we get back an equation very similar to what we had earlier for 1D, right. And then again we use my heat conduction law, which tells me that the flux is proportional to the negative of the temperature gradient, and then I substitute that there. I get divergence of K kappa times gradient of T, right. And in case kappa is a constant, in case of constant conductivity kappa, I can pull that kappa out. So, I get kappa times divergence of gradient of T, which is nothing but Laplacian of T. So, kappa times Laplacian of T. So, rho C del T is equal to kappa times Laplacian of T, which becomes my heat conduction equation in 3 dimensions, right. So, solution methods. We will consider 2 methods to solve the diffusion equation analytically. The first method involves using the eigenfunction approach, which we described earlier for the wave equation. In the second approach, we will use Laplace transform, right. We will use Laplace transform to solve the problem effectively, right. So, the first one way is to use the eigenfunction approach, the other way is to use the transform based method. In this case, we are going to use Laplace transforms to solve that problem. To consider the problem, so again when we looked at the wave equation, the first problem we looked at was we considered wave propagation in a ring of unit circumference, and we looked at that condition. And now again when we look at the heat flow problem, we are again going to look at that geometry. So, we are going to consider a ring of unit circumference, and we are going to consider heat flow along that ring. And as we noticed in case of the wave equation, for this particular geometry, the boundary conditions are periodic, right. So, if I have along, if my spatial dimension is my arc length along that ring, once it completes one whole arc length, and since the circumference is 1, once it travels through 1, right, I must get back the same boundary conditions, right. So, it has got periodic boundary conditions which tell me that the temperature at 0 must be equal to the temperature at 1, must be equal to the temperature at n. Every time I am going route 1, 2, 3, I am reaching the same point. So, at the same point the temperature had better be the same. So, T0, T1, T must be equal to T and T, and similarly the slope, right. Here the slope, when I say slope, when I say prime, I denote partial derivative with respect to the x, right, where x is my distance along the circumference of the ring, right. So, T prime 0 T must be equal to T prime 1 T and T prime n T. So, that is I know what is my governing equation, those are my boundary conditions, right. So, in this case let us do when I looked at the wave function, when I looked at the eigenfunction approach for the wave equation, I sort of assumed that you would know how to find the eigenfunctions, but I think that for this particular problem I will go through it in detail, right. How do you find the eigenfunctions? Let us go through that in detail, right. So, to find the eigenfunctions, we assume solutions of the form T is equal to E n x e to the power minus lambda n kappa of T, and substituting this in my governing equation, which was somewhere, which we have left long back here. If I substitute that particular form of my T in this governing equation, I get an equation like this: d2 en x dx square equal to minus lambda n en x, right. I get an equation like this, and it has these boundary conditions, which are that en 0 must be equal to en 1, en prime of 0 must be equal to en prime of 1. So, this becomes my eigenvalue problem. How do I get my eigenvalue problem? Well, I do this substitution, right. I assume that T is of this form, right, where n is my eigenfunction and this is my time dependence. I assume my time dependence of this is of this nature. If I substitute that, I get this equation, and then again, so you can see that this is an equation in x, right. So, I assume that my eigenfunctions are of this form. So, this equation now I assume is of the form e to the power minus I omega x, right. And then once I substitute that here, this differential equation becomes a algebraic equation in omega, right. I get an algebraic equation in omega, and thus I get lambda n equal to plus minus omega, right. So, my solution E n x is equal to e to the power minus I omega x. So, using de Moivre's theorem, right, I know I can write it as a cos omega x plus b sin omega x, right. So, E n x is of this form, right, and omega is related to lambda, the eigenvalue, like this, right. This is of the we have seen that this is like an eigenvalue problem, right. I have a linear operator and times some constant operating on that same function. So, this is of the form of an eigenvalue problem where lambda n is the eigenvalue, and I know the solution of this equation is of this form, right. So, if E n is of this form, then E n prime had better be this. I have just taken derivative with respect to x, and then I impose my boundary conditions. What are my boundary conditions? The E n 0 is equal to E n 1. So, evaluate E n at 0, equate that to E n at 1. So, that gives me the top equation 1 minus cos omega a minus sin omega b equal to 0, and then I evaluate E n prime, I evaluate that at 0, and I also evaluate that at 1 and set them equal. So, I get the bottom equation omega sin omega 1 omega sin omega a plus omega 1 minus cos omega b equal to 0. So, now I have a linear system and a homogeneous system to get non-trivial solutions for a and b, that is to get solutions when a and b are not both equal to 0. The determinant of that system must vanish, right. Determinant, if I evaluate the determinant of that system and set it equal to 0, I find eventually I get this equation cos of omega equal to 1, and I know that cos of omega is going to be equal to 1 for omega equal to 2 n pi, n is equal to 0 plus minus 1 plus minus 2 up to plus minus infinity. So, that gives me my omega. Omega I know is equal to my eigenvalue. So, I already know my eigenvalues, right. I already know my eigenvalues. So, I know my eigenvalues. I know now I know my eigenvectors, right. I know my eigenvectors up to those constants, right, up to those constants a and b, right. So, I know that. So, my eigenvectors must be of the form E n x is equal to e to the power minus 2 pi I n x. Why is that? Well, I said that E n x is equal to minus I omega x, right. So, omega is given by that. So, I know my eigenvectors, and thus I go back and remember that this is a self-adjoint operator. This is a self-adjoint operator. So, its eigenfunctions form a basis, are complete, they form a they are complete. So, they form a basis for that function space. So, my solution T x t, I can always express them as a linear combination of my eigenfunctions. So, this T x t must be equal to the sum of this t tau n t, which are some coefficients, times my basis functions, which are my eigenfunctions, and I can evaluate these constants, these coefficients, which are functions of time, by using the orthonormality of the eigenfunctions, right. So, maybe this is a good place to stop, and we will continue our discussion the eigenfunction solution for the heat equation. We will talk of the Laplace transform solution, and then we will move on to our last remaining type of second order linear partial differential equations. Those are elliptic equations. Okay. Thank you.